Welcome to my presentation. My name is Steven Bervoets, and I've been working for 8 years as a controls engineer for Punch Powertrain. I would like to start with a short movie. So what you see here is a car that's equipped with our previous generation of our electric powertrain. And in this presentation, I will show you how we have boosted it from 70 kilowatt to 130 kilowatts. At the same time, we have reduced the noise and the cost, and we will improve the comfort for the driver. Stephen explained this morning that InMotion develops the racing car for the future, and you can see it next door. We develop the electric powertrains for passenger cars for the future. First, I will show you the company that I'm working for. Second, I will explain you the project that I'm working in. I will show you the design workflow that we follow with a model-based design. Also, the motor technology will be explained. I will show you how we integrated the MATLAB tools into our workflow. And finally, I will show you the results. So Punch Powertrain, it's a Belgian company. Our headquarters is in Sint-Truiden. We also have an R&D office in Eindhoven. We have a small after-sales office in Malaysia and an assembly plant in China. We are an independent supplier of clean powertrains. It all started with DAF. That's the car you can see one floor lower at the staircase. That was produced by DAF in 1972. That's when our company was founded. Then we had a really difficult situation. We always had one customer in Europe for the CVT transmission, and due to that we had different owners because they didn't really believe in the company. In 2006 we became Punch Powertrain, and the current CEO, he focused on the Chinese market. And at that time, all the Chinese people, they started buying their first car. And you may know it or not, but they're with a lot of people. So that's a really booming market. And from then on, the growth was really incredible. So when we started, we produced 30,000 transmissions per year. Now, 10 years later, we make 30,000 transmissions per month. We also have now more than one product, but I will explain that later. And that growth you can also see with the number of employees. Just after the crisis in 2009, we were with 130 people. This year, we'll hope to land with 700 people. But for that, we still need to fill in 66 vacancies. So if any of you is looking for a new job, just come to me after the presentation and I'll give you a new job, if you're good enough. By 2020, we want to end up with 1,200 employees. So that's also with the number of employees, the tenfold within 10 years. The automotive landscape has many different powertrains, ranging from fully conventional combustion engines all the way to full electric vehicles. And Punch Powertrains provides multiple solutions to accommodate all these different types. Our transmissions can be used in a conventional car all the way up to a full hybrid. We also develop electric hybrids that can be used from mild hybrid to a range extender. Currently, we have an application project, so that's with a signed customer to go into production for the plug-in hybrid. Our electric drives, they can be used in an electric vehicle, of course, but if you use them in a through-the-road concept, they can also be used in a full hybrid car. For the electric powertrains, we have a single-speed transmission, we also have a twin-speed transmission, and we even have a transmission where we can use two motors and combine them in one single-speed transmission. We also do some research on flywheel-based transmissions. That's to be cost-effective because the batteries are still very expensive, and if you can store the energy in mechanical speed that's more cost effective than a battery. Now I would like to show you the project from which I will be presenting the results today. It's a European Union funded project called ARMEVA that stands for Advanced Reluctance Motors for Electric Vehicle Applications. It has partners from all over Europe, and we've been working together quite intensively. And the goal of the project is to develop a new generation of rare earth-free electric motors, so that means no magnets, based on magnetic reluctance. The content of this project is to develop a complete drive system. That means a motor, power electronics, and controls. And to be competitive in the future, the focus lies on an increase in power density and an increase in efficiency. And to reduce the cost, we integrated the motor and the power electronics within the transmission. In the past, we had a transmission, we bolt the motor to it, and then next to that, we had a casing for the power electronics. In this project, we integrated everything into one package. Now, why would the European Union be interested in funding a project like this? Well, that is because with the outcome of this project, we can build electric cars at a lower cost with an increased efficiency. You may know a famous Californian company producing EV cars. Well, I see the gentleman smiling. That's like a high-end iPhone on wheels. It's not yet affordable for everyone. What we try to do is build an Android on wheels, so the OEMs can integrate our systems into more affordable cars. And that will lead to more electric vehicles, which is good for everybody. Now, developing an electric powertrain, how do you start on it? Well, this is the design workflow that we have used for this project. First of all, we start with the vehicle requirements. For that, we built a high-level model. That model can be further refined to determine the e-drive requirements. And the step after that was that we simulated 3 different motor types to determine the best one. These motor models were used to do the electromagnetic design, but also to help the other partners to design within their own domain. One example is that we have simulated the main cost drivers of the final product. And for that, we did a sensitivity analysis of the switching frequency. So we used the model of the complete system to determine how low we could go with the switching frequency that results in cheaper IGBTs. So we have designed 3 different reluctance motors. A reluctance motor is part of the family of the synchronous machines. And these 3 motors were designed by 3 different partners in the project. In the end, the 3 models had to come together because when we were building a prototype, we only wanted to build one. It would not be feasible to build prototypes and cars for the 3 types. The comparison we did based on cost, efficiency over a drive cycle, and noise. So to be able to do a fair comparison, we needed the simulation models in quite a high detail, because for the cost, you need to know all the components, the sizing of all the components, so as well as mechanical as electrical. To be able to calculate the efficiency over a drive cycle, you need to know the losses in detail of the different motors, and that you can then apply back to your vehicle model. And for the noise and the vibrations, you need to simulate the forces that result from the control strategies and the mechanical design. In the end, it was the switch reluctance motor that had the highest overall score. Is there anybody in the room that knows how a switch reluctance motor works? One guy, maybe you can explain. So a switch reluctance motor is characterized by its double salient structure. That means he has discrete rotor poles and stator poles. It's driven by a reluctance torque. What that is, you can compare to an electromagnet. So if you energize the coils of the stator, you generate a magnetic field, and the torque is then produced by the tendency of the rotor to move towards a position where you have the smallest air gap. All the benefits from this motor result from the fact that the rotor is just a simple block of laminates of steel. The high speed capabilities, the robust construction, the low cost. Now you might think, why is not everybody using a stretch reluctance motor then? Well, that's because due to the physical properties, it has quite a high torque ripple. And also the noise that it generates is really not pleasant if you don't counter it. If you have to solve these problems with really high non-linear behavior of the motor, you get quite a challenging job in designing the controls and the power electronics for the motor. The sound you just heard is from the first generation of these motors. You might be able to stand it for 10 seconds, but if you're on the highway, you really don't want this in your ear buzzing all the time. I would love to show you also the sound that the Armiva motor produces, but it's so quiet it wouldn't make any sense to show it here. Next, I would like to translate these challenges that are inherited from an SR motor and apply them to the challenge we had within this project. Within this project, we decided to double the maximum speed up to 20,000 RPM. That means you have less time to put the current in the coil within the optimal time frame. And to counter that, we had to reduce the inductance. In the end, we ended up with an inductance that leads to a current rise time of 8,000 amps per millisecond. That means that in your software or your hardware, you have a delay of 1 microsecond, you already get an error of 8 amps. In the previous designs, we always used the processor, and even with the simplest control strategy, so normal hysteresis control, you just measure the current. If it goes above a certain limit, you switch to IGBT. That simple piece of software already takes 14 microseconds. If we would use that in the Armiva motor, we would get an error of more than 100 amps, which is just not usable since the maximum current rating is 450 amps. And that was not the only challenge we had in Armiva. We also wanted to use new innovative control strategies like direct torque control. And there, within one time step, you have to take the current in one phase, combine it with the position of the rotor, do that in a lookup table, then you get the torque that phase is producing. That you have to do 3 times in parallel for the 3 different phases. And then calculate the optimal switching strategy. Excuse me. Now, I don't know if everybody completely understood what I just tried to explain, but I think you can imagine it's just not going to work if we would use that processor from the past. Therefore, we decided to use an SoC device. That's a processor that's glued together with an FPGA. We've chosen the Zynq device, and that leaves us one more challenge. We have nobody in Punch that can program an FPGA, and that's when we knocked on the MathWorks door. Stefan explained to you just before the break how that the workflow works to generate code for the FPGA and the processor. The principle is you just design your control strategies within MATLAB, and the part for the processor you can compile. The part for the FPGA, you first need to set all the data types correct. That's done by a tool called the fixed point workflow. That tool really takes you by the hand. It runs based on the simulations that you run, it gives you a proposal for the data types. You can accept them, rerun your simulation and validate the accuracy. You might need to do some small modifications, but the starting point is already quite good. The next step is that you generate code for the processor that's with the embedded coder. The FPGA is done with the HDL coder. And finally, for the FPGA, you need to use a tool called Vivado to generate the bitstream. Now I would like to share with you the experience of a first-time SoC user such as myself. From the past, we had a big part of the control models already available for the processor, and I found it really easy to make the modifications for the new architecture. We just took some blocks and put them in the processor part, and the other blocks we used for the FPGA part. I was also very amazed by the AXI bus. That is the communication protocol between the FPGA and the processor. It really works out of the box and it's really fast and reliable. So you can transfer a lot of communication, a lot of data between the processor and the FPGA. I was also surprised that something that's very standard within automotive was not available out of the box. The CAN bus. We had to develop our own drivers. We didn't really have time, so we asked the MathWorks consultancy and they implemented it very quick. So the ecosystem is not completed yet, but it's growing as we speak. The fixed point workflow, which I just told you about, it's very straightforward, but it still does consume quite some time. I think you can compare it to the way we program processors, the transformation we've seen over the last 10 years. 10 years ago, it also took quite some time if you made embedded software to get all the data types correct. And these days, the processors, they just run in a floating point. So you take your model, you compile it, and it works. I hope that within the next 10 years, we can see the same transition for FPGAs. We just work on the control strategy, and the compiler does the rest. But we're not there yet. So Vivado is a really powerful tool to generate a bit stream. It does all the routing in the FPGAs, really fancy, but we didn't really open the program. The only thing we had to do is install it and pay the bill, and everything works just behind the scenes. My next slide is about how we did the validation. So in the beginning, I showed you how we handled the design. Now I would like to show you how we did the validation and how that our development workflow made it very easy because we did a lot of reusing of existing models. When you design your control strategies in a model-based design way, then actually you've already built your mill model. So that one you get for free. The next step we did was to test the communication protocols in real life, so with real hardware. Now the final hardware was not yet available, but the Zynq platform, they have some evaluation boards available so that we could just test on our own desk to validate the communication. The next step is to go to the hill. That was also quite fast implemented, the hill model, because we had it still available from the previous generations, and we could combine all the new things from the models we produced when we were defining the requirements. So the combination of those two gave us a very fast hill model. At first, we also used the hill with the development board because the final hardware was still being produced by the other partner. And due to the fact that we could already do a really in-depth validation of the software, we needed a very short time when the final hardware was produced on the hill to validate it before we could go to the test bench. It's a similar story as FinTech told you before the break. The fact that we had a thorough validation before we go to the test bench also gives the advantage that you don't blow up too many prototypes when you're at the test bench, because that really delays your project and it costs a lot of money. The current status of the project is that we are, since last Friday, we are finally producing torque on the test bench. And in the coming weeks, we'll do BMW the honor of improving their i3 with a brand new Almeva powertrain. Then finally, I would like to share with you the result of the project. In the back, you have the part which I'm not allowed to show you from our IP director. That's the motor covered with its cooling jacket. And nicely around that, you have wrapped the capacitor, the power electronics, and the rest of the electronics with the software. So everything is inside this package. On this platform, we have developed 4 different control strategies with only 2 people in 1.5 years. That would have never been feasible without the current state of the tool chain. If we would have done this project 5 years ago, it just wouldn't work. Definitely not without the FPGA experts. All the models that have been produced for this A-sample phase, so the prototyping phase, we don't need to throw them away after this phase. We can reuse them to go all the way into production. So that's the part that Stefan explained, that you can reuse the same models and implement them on different targets. Due to this development progress of reusing already validated models, we had a very smooth integration and validation phase. Like the fact that I showed you that we could validate the software even before the power electronics were available. This very fast development cycle is also very important for the other projects within Punch. As I've showed you in the beginning, we are growing like crazy. We have a lot of new colleagues that have to implement a lot of new products. The Chinese market is also very strict on the time to market, and the quality always has to be better. The shocks that you could feel in the old cars, they just don't accept it anymore. I have a good example of this time to market, because last year the Chinese government, they decided that the fleet average consumption of every OEM has to be within a certain target by 2018. And that's not a lot of time. If the OEMs don't meet that target, they might lose their license to produce cars. And the target is very strict, so they cannot make it without hybrid or electric vehicles. So the Chinese OEMs, they all started panicking because who can make a hybrid car within only 3 years? And that's where you need this very fast development cycle and the reuse of existing models to validate your product throughout the cycle is just a necessary tool to get a first time right approach. So I hope you enjoyed my presentation, and if you have further questions, I will be available after the